Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 11, Lesson 7 on quadratic models. Before we begin, let me remind you that you can find a worksheet and a homework assignment that go with this video by clicking on the video's description or by visiting our website at www.emathinstruction.com. Also, don't forget about those QR codes. I know I've reminded you enough, but they're at the top of every worksheet, and you can use them with your phone or a tablet to scan them and be brought to the video that goes right along with that lesson. So take advantage of that, all right? Let's begin. All right, so we've really studied three major types of functions in this course: linear, exponential, and quadratic. There have been other ones: absolute value, square root, cubed root, step functions, things like that. But what we want to do today is revisit quadratic modeling one more time. So let's start off with a problem that gives us a quadratic model. Exercise 1. Projectiles that are fired vertically into the air have heights that are quadratic functions of time. A projectile is fired from the top of a roof. Its height, in feet above the ground, that shouldn't be an apostrophe there. Its height in feet above the ground after t seconds is given by the following function. H of t equals negative 16 times t minus 2 squared plus 144. All right, so there's our model, right? And make sure that you really get it. The input is the time in seconds, and the output is the height of the object above the ground. So in letter A, it says evaluate h of 0. Using proper units, explain the physical significance of this answer. Pause the video now and try to do this. All right, well, let's do it. Okay, so h of 0 is going to be negative 16 times 0 minus 2 quantity squared plus 144. All right. If we crank through that, that's negative 16, negative 2 squared is positive 4, plus 144. The question is really how much of this are you going to do before you let the calculator take over? But we end up having 80. 80 what? 80 feet. Right? So there's our h of 0. But what's the physical significance? The ball was fired from a height of 80 feet. All right, letter B. Determine algebraically the time when the ball hits the ground. All right, so great. How do we do this? Well, when the ball hits the ground, the height must be 0, right? So that would be negative 16 times t minus 2 squared plus 144, that is the height, and that height must be 0. We can now solve this quadratic by just simply applying inverses. Remember, 2 has been subtracted from t, then it's been squared, then it was multiplied by negative 16, then we added 144. So we'll begin to solve this by subtracting 144 from both sides, right? That would give me negative 16 times t minus 2 squared equals negative 144. I can then get rid of the negative 16 by dividing by negative 16 on both sides, right? I'll come up here, t minus 2, quantity squared, is going to be equal to 9. Now I get rid of the squaring by taking the square root of both sides. Don't forget though, 9 has 2 square roots, right? It has plus or minus 3. So that means I really have two equations to solve. Either t minus 2 is negative 3, or t minus 2 is positive 3. Solving this one by adding 2 to both sides, I'll get t equals negative 1. Solving this one by adding 2 to both sides, I'll get t equals 5. Now, we're going to reject the t equals negative 1. Not because you can't have negative time, okay? You can most certainly have negative time. Negative time just means things that have happened in the past. But we fired the ball at t equals 0. It's not going to hit the ground before we fired it. So it hits the ground at 5 seconds. Now, letter C says create a graph of h of t on the grid provided. All right? So to do that, ideally, what we would do is we would open up our TI-84 Plus and we would create a table of values and then we would graph the thing. All right. For right now, to try to make one of our last videos a little bit shorter, what I'm going to do is I'm going to just generally sketch what the graph looks like. But we would just put that into y equals. We would bring our table open. I think I'd actually maybe make my table go by 0.5 instead of 1.0 because these things are 0.5 and 1.5, etc., right? But what we would see is we'd see a graph that kind of looks like this. We know exactly where it starts. It starts at 80 feet. And then after a half a second, it's just a little bit over 100. At 1 second, it's up here at about 130, a little bit more. At 2 seconds, it's up here just a bit above 140. At 3 seconds, it's at, at 2 seconds, it's at 144. And then what happens is symmetry starts to kick in. We start to get a graph that looks like this. All right. In fact, at 4.5 seconds, right, we're just barely over 40. And at 5 seconds, we know we've hit the ground. So our projectile path looks something like this. I want so badly not to botch one of the last parabolas I'm drawing. It's not great, but hopefully it gets the job done. Letter D. What is the maximum height the projectile reaches, and at what time does it reach that height? Well, it's right up here. All right. And the maximum height, which I'll call h sub max, ends up being 144. And it occurs, no question about that, at t equals 2 seconds. Can we see that in the vertex form? Sure we can, right? It's been a little while since we worked sort of intensively with quadratics in their shifted or vertex form, but there's our 2 and our 144. All right? So please excuse me for not opening up the TI-84 Plus and setting up the table. I didn't have a lot of room on here, and we've done that so much that hopefully you can get practice on that on your own. Anyhow, pause the video now and spend whatever time you need writing down the information. All right, I'm going to clear it out. Let's keep going. Exercise 2. We've got a little popcorn going on. Popcorn has an optimal temperature at which it pops. This is actually very true, right? You know, too cool of a temperature, not enough pops. Too hot of a temperature, it burns, not enough of it pops. Food engineers at Perpetual Popping study the percent of popcorn kernels that pop at a certain temperature. Who writes this stuff? That would be me. Their data is shown in the table below. Okay, so let's just make sure we understand the data table. At 385 degrees, 38% of the kernels pop. At 410 degrees, 68% of the kernels pop. All right, so that's how we're interpreting this. All right, letter A, why does a quadratic model seem reasonable given the data in the table? So what would you write down for that? Why does the quadratic model seem reasonable? All right, in a certain sense, you almost want to ask, why doesn't a linear or an exponential model work well, right? Linear and exponential models either always increase or they always decrease, as we talked about a couple lessons ago when we reviewed them, right? But quadratic models have turning points, right? So this, well, actually, let me write it this way. I'm going to say the outputs increase and then decrease. And that's why a quadratic model would work well. Or, better yet, why it would be reasonable. I don't know if it really works all that well. Anyhow, let's take a look at B. In letter B, it says, if the engineers model the percent popped, P, by the equation P equals -1/100 times, etc., Then at what temperature is the greatest percent of popcorn popped, and what is the greatest percent? So here we're just looking for a straight up numerical answers. Pause the video now and see if you can figure this out. All right, well here we have a quadratic in its vertex form. And as we all know, quadratics in their vertex form, random mark, quadratics in their vertex form are very easy to see the turning point. Right here is the temperature where we're going to get the greatest level. So the temperature is 450 degrees Fahrenheit. And we can kind of see that in the table, right? I mean, here in the table, 440 is the best, but that doesn't mean it's actually the best overall. It's just the best in the table, right? And the highest percent is 82%, and that's right here. The vertex, right, can always be identified when it's written in vertex form, and because the A is negative, this is a quadratic that has a maximum, right? All right. It's been a little while since we've seen this stuff. It has, which is why we wanted to review it in the last unit. All right, pause the video now and write down anything you need to. Then we're going to do one last big modeling problem when it comes to quadratics. Okay, so far I've given you the quadratic models, but the real power is you coming up with the model on your own. All right, so that's what we're going to work on in the last problem. Shayna is creating a garden that has 3 equal-sized rectangles separated by wire fencing. Okay. She has 160 feet of fencing and wants to construct the garden as shown below. So just to be very clear, we've got this garden and there's fencing everywhere you see lined segments. So not just around the garden, but also fencing dividing it off here and here. All right, Shayna decides to designate the overall width of the rectangle as x, so that's the overall width, and the overall length as y, as shown in the diagram. How much area would the garden contain in square feet, so the whole garden in square feet, if the width, x, was 10 feet? What? Show the calculations that lead to your answer. So pause the video right now and figure this out. You can do it. By only knowing the value of x, you can figure out the entire area. You also need to know that she's going to use 160 feet of fencing, but you can figure out the entire area of the garden. Pause the video now and try to come up with this. All right, well, let's see how it's done. Now think about this, right? We've got 10 feet of fencing here, then we'd have 10 feet of fencing here, 10 feet of fencing here, and 10 feet of fencing here. So we'd have 4 times 10, or 40 feet of fencing that would get used up in there. Well, how much fencing would we have left? Well, we started with 160 feet, subtract off the 140 feet, we would have 120 feet left to divvy out for the 2 values of y. But we would have to divvy it out amongst 2 sides, so that would be this dimension. So we'd have 60 feet here and 60 feet there. But that means the overall area, which is just length times width, would be 60 feet times 10 feet, which would be 600 square feet. Cool. No problem. All right. Letter B. Write a formula for the overall area A of the garden in terms of x and y. So this doesn't have anything to do with letter A, okay? This should be a very simple formula. Well, try this on for size. Area equals x times y, right? This length times this length will give me the overall area. But that is a formula that has 2 inputs, both x and y. What I'd like is a formula with only one input. So that's what we're going to do in part C and part D. In part C, it says write an equation for the relationship between the width x and the length y based on the fact that there's 160 feet of fencing. Solve this equation for y. All right? Pause the video now. See if you can do that. All right, well, here it is. I'm going to do this in red just to contrast it with the blue that's on the screen. This was an x, this was an x, an x, and an x. So what did we have? We had 4 of those x's, then we had a y and another y, and all of that has to add to be 160. So there's an equation that relates x and y, but then it says solve this equation for y. So I'm going to subtract 4x from both sides, and I'm going to get 2y, and I think I'm going to put the x first. You'll see why this is eventually. So 2y equals negative 4x plus 160. Then I'm going to divide both sides by 2. I'm going to run out of room. Then I'm going to distribute the division by 2. So I'm going to divide the negative 4 by 2. And I'm going to divide the 160 by 2. And I'm going to get y equals negative 2x plus 80. Now I do want to emphasize that if you have y equals 80 minus 2x, it's completely wrong. No, it's not. If you have y equals 80 minus 2x, it's beautiful. It's really well done. Right? That's just that commutative property of addition. All right? But watch what we can now do in letter D. Letter D says find an equation for the area, A, only in terms of the width, x. That's going to be an easy thing. Right? The area is x times y. But y is negative 2x plus 80. So we're going to use the principle of substitution of equals to get rid of that y. See, if y is equal to negative 2x plus 80, then there's nothing wrong with putting this in. And that's perfectly good. But since I'm working with quadratic models today, I'm going to actually distribute that. X times negative 2x is negative 2x squared. And 80 times x is 80 times x. And there is a beautiful equation that gives me my area if I know what x is. What's really cool is you could actually now take x equals 10 and you could check it in this model to see if it gave you the 600 that we got in part A. That would be a very good check. But we're going to actually move on. So pause the video now and copy down what you need to. Okay, I'm going to clear out the text. Hopefully I'm bringing some of this stuff over to the next page because we're not done. All right. Now, letter E says, using your calculator, right, sketch a graph of the area function you found in letter D. And just like what we did before, normally what I would do is I would open up the TI-84 Plus at this point, and we would sketch the entire thing out. What I'm going to do is ask you to forgive me on that, and I'm just going to plot it out a little by little. But you would open it up, you would put that into Y1, you'd generate a table of values. Please note I would probably have the table go by 5s because that's what's going on down here on the x-axis, right? And if I did that, what I would find is that when the width is 0, the area is 0. And when the width is 5, the area is 350. When the width is 10, the area ends up being 600. When the width is 15, the area ends up being right around 750. When the width is 20, the area ends up being 800 on the dot. When the width is 25, we start getting back into that symmetry. The rest of it just pans out symmetrically. And we get a beautiful, beautiful quadratic model. Probably the last parabola I'm going to draw. Come on. Wow, well, going up it looked okay. But there's our sketch. Again, please excuse me for not opening up the TI-84 Plus. I want to keep some of these last videos a little bit shorter if I can. Letter F. What is the maximum area that Shayna can enclose with the 160 feet of fencing, and what dimensions should she use? Well, it's pretty obvious to me that the max area equals 800 square feet. Don't forget those units. Don't say 800 feet. That doesn't make any sense. It's not an area. What dimension should she use? Well, I know x should be 20. All right, but what I don't know is y. And yet, we had an equation on the other side of the sheet that said y was equal to negative 2x plus 80. Remember that? So, if I know that x is 20, then I can find negative 40 plus 80, and I can find that y is 40 feet. So I should have a rectangle that looks like this. Of course, it's got those other two dividers in there, but its overall dimensions are 20 feet by 40 feet. Isn't that cool? All right, so we created a quadratic model all on our own. Anyhow, pause the video and copy down anything you need to. Okay, clearing out the text. All right, let's wrap up. So mainly what I wanted to do in this lesson was review the basics about quadratic models. How you can look at a quadratic model, why they're used when data increases and then decreases or vice versa. How you can look at the vertex form of a quadratic model and see that turning point. And the final problem we did was we actually created a quadratic model based on, if you will, roughly speaking, perimeter and area. For now, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time,